Hello students. So we'll continue our discussion on alkyl and aryl halides. So in the last session we had discussed about the alkyl halides and their preparations and their properties. So in this session we'll be discussing concepts related to aryl halides. Now, so what are aryl halides? These are the compounds in which halogen atom is directly linked to the benzene ring. If it is directly linked to the benzene ring, we refer them as aryl halides. Now, so let us see the preparation of aryl halides. Aryl halides can be prepared from phenols. It can be prepared from diazonium salts also. Let us discuss first the preparation of aryl halides from phenols. Yeah. Now, so phenols are the compounds in which hydroxy group, that is OH group, is directly linked to the benzene ring. In phenols, the lone pair of electrons that are present on oxygen atom, okay, will be involved in resonance with the benzene ring. Okay, whatever the lone pair of electrons that are present on oxygen atom will be involved in resonance with the benzene ring. As a result, this oxygen and this carbon acquires a partial double bond character. Because of this resonance, the oxygen carbon bond will acquire a partial double bond character. Okay, since it acquires partial double bond character, so it is not easy to break this carbon oxygen bond. So the carbon oxygen bond cannot be broken easily, or the cleavage of carbon oxygen bond is difficult under normal conditions. That is why the aryl halide prepared by replacing this oxygen atom, okay, so it will be produced in very low yield. The yield of product in such reaction is very low, okay, because of this carbon oxygen bond which acquires a double bond character. But still, however, phenols when treated with phosphorus pentachloride, PCl5 undergoes substitution to give chlorobenzene. Okay, you get chlorobenzene, okay, plus the OH. H will combine with Cl to form HCl. So POCl3 is obtained. Phosphorus oxychloride will be the side product. Okay, this is how the haloaryls, I mean chlorobenzene, can be prepared from phenols. Okay, but the product obtained will be in very small quantity. The yield is very low in such reactions. So another important method of preparation of these haloarenes, okay, haloarenes, is from the diazonium salts. So haloarenes can be prepared from diazonium salts. Okay, let us see what we mean by this diazonium salts. See, if we have aniline, it's not always aniline, any amine. I have taken an example of aniline because the diazonium salts of this aniline are generally stable, I mean aromatic. So when this aniline is treated with a mixture of NaNO2 and HCl, okay, generally at low temperatures, okay, 0 to 5 degrees Celsius, okay, so this group undergoes diazotization and it forms this compound, that is N2 plus Cl minus. This compound is called as diazonium chloride. Okay, we call this compound as diazonium chloride. So a mixture of NaNO2 and HCl will produce HNO2. Nitrous acid is what we call it as. So this nitrous acid reacts with NH2 to form this diazonium salt. So this diazonium salt can be substituted easily. Okay, a nucleophile can easily attack this carbon because the nitrogen is positively charged. It will be pulling electron towards itself. As a result, this carbon will acquire a positive charge, and the attack will result in the displacement of a stable nitrogen molecule. Okay, so replacement of N2 group, this group will be very easy. So hence amines are converted into diazonium salts, and then the nucleophilic substitution is carried out. Okay, you can prepare this haloarenes by from diazonium salts. So this is a very important method of preparation. Okay, now let us see what is generally done. Okay, this diazonium salt, that is, which is produced by the diazotization of aniline, diazonium salt is treated with HCl in presence of copper salt, CuCl. Okay, Cl minus displaces this N2. You get chlorobenzene, N2 goes off. Okay, so if you want chlorine here, if you want to substitute that N2, that means the diazo group by chlorine, you need to use HCl. You need to use HCl. A simple nucleophilic substitution takes place. A simple nucleophilic substitution takes place. Right? Now, if you want to substitute it by bromine, you have a diazonium salt here, N2 plus Cl minus. If you treat this with HBr, in presence of cuprous bromide and corresponding halogen acid. If you want chloride, use HCl. If you want bromide, use HBr. So you get bromobenzene. Bromobenzene is what you get. Okay. So simple substitution of this diazonium salt, nucleophilic substitution of this diazonium group results in the formation of the corresponding haloarenes. So aryl chlorides and bromides are obtained by treating this diazonium salt solution with cuprous chloride or bromide in corresponding halogen acids. Okay. This reaction is referred as Sand-Meier's reaction. This reaction is called as the Sand-Meier's reaction. So very important reaction, this is, students. This reaction is referred as Sand-Meier's reaction. In Sand-Meier's reaction, it is the halogen atom that is linked to copper which links with the benzene ring. This halogen atom links with the benzene ring. Okay, now So there is the modified method of the above reaction, which is called as the Gattermann reaction, which involves the use of copper powder instead of cuprous chloride or bromide. It involves the use of copper powder instead of cuprous chloride or bromide. That means diazonium salts. Diazonium salts, N2 plus Cl minus. If it is treated with HCl in presence of copper instead of copper salt, you get the corresponding chlorobenzene. If this is treated with, if this diazonium salt, that is N2 plus Cl minus, is treated with HBr in presence of copper, instead of cuprous bromide, you get bromobenzene. This reaction is called the Gattermann reaction. This is the modified version of the Sandmeyer's reaction. Okay. If you want to prepare aryl iodides, take diazonium salt and just treat it with potassium iodide and simply warm it. You get corresponding iodobenzene. Iodobenzene is what you get. Okay. This is the method of preparation of haloarenes from phenols as well as diazonium salts. A very important method this is right now. Let us move on with the properties of these aryl halides. We'll discuss the properties of aryl halides or the reactions of these aryl halides. Chemical properties is what I mean. Aryl halides undergoes nucleophilic substitution reactions. Okay, they undergo nucleophilic substitution reactions. Okay, now. But the replacement of this halogen atom is not so easy. The reason is the lone pair of electrons that are present on halogen atom will be involved in the resonance. As a result, the carbon-chlorine bond acquires a partial double bond character. Hence, cleavage of this carbon-chlorine bond is not so easy. So hence, the nucleophilic substitution reaction is what we say. They occur under extreme conditions. That means under drastic conditions. Okay. Let us first deal with the reaction with NaOH. Chlorobenzene, when it is treated with NaOH at a temperature of 573 Kelvin. Look at the temperature, students. 573 Kelvin, that means around 300 degrees Celsius. Okay, 573 Kelvin, and the pressure required is 200 atmospheric pressure. So the pressure required is around 200 atmospheric pressure. Okay, so you get phenol. You get a phenol, right? So look at these conditions. So this replacement of this Cl atom is not so easy. So chlorobenzene when treated with NaOH at 573 Kelvin and 200 atmospheric pressure will give you phenol. So when chlorobenzene is treated with NaOH, you get sodium phenate generally. So you need to acidify this. So I'll just write the reaction in detail. So chlorobenzene, when it is treated with NaOH at this temperature, that is 573 Kelvin and 200 atmospheric pressure. So OH displaces this Cl. But you know that phenols are acidic in nature and we have base in the solution. So sodium phenate is formed. So this on acidification will give you phenol. This is the complete reaction is what I can say. So it forms sodium phenate. Why? Because once it forms phenol, whatever the NaOH that is present, the base will convert it to salt and then you should acidify it. Then only you will get phenol. So if an electron withdrawing group like NO2 is present at ortho or para position, the reactivity of these haloarenes increases. Take this chlorobenzene. We'll take chlorobenzene. Okay. If there is an NO2 group here, and you are treating it with NaOH, and second, what you are doing, you are going for the acidification, right? So the temperature required is 443 Kelvin. The temperature required is 443 Kelvin. Look at this. The presence of NO2 group has increased its reactivity. See, if there is no NO2 group, the temperature required, what was the temperature required? The temperature required was 573 Kelvin. Now the temperature required is 443 Kelvin. The same reaction. That means NO2 group, that is electron withdrawing group, if present, increases the reactivity of these halogens. As the number of NO2 group goes on increasing, the reactivity increases. For example, take chlorobenzene containing 2 NO2 group. As usual, first step is treating it with NaOH, second step is H plus ion. Here the temperature required is 368 Kelvin. So as the number of NO2 group goes on increasing, the reactivity also increases. That means, and the NO2 group, that is electron withdrawing group, what it generally does is it stabilizes that. So whatever the intermediate form, it stabilizes that, because when OH minus attacks here, so when the electron, they move here, so this electron withdrawing group, they pull those electrons and they stabilize the intermediate. That is why the presence of NO2 group increases the reactivity of this chlorobenzene. Right? So students, in this session we have discussed two things here. One is the preparations of haloarenes. Other one is one of the reaction of haloarenes. Okay. In the next session, we'll continue the remaining part. Thank you.